This is Mike Donaher, and this is my final report for Project 2, Correlated Q Learning. This was the game in question that we had to evaluate. It was a grid soccer game where it was a zero-sum game. If agent B or A got to their desired goal, they would get plus 100, and if they had to be in possession of the ball. And if they went into the opposing goal with possession of the ball, the rewards were reversed. They would get minus 100, and the opposing agent would get plus 100. These were the charts we were tasked with recreating. The first three are joint Q learning charts: correlated Q, utilitarian, faux Q, and friend Q. And the last chart was just the Q learner for agent A taking the action of moving south. So the first three have the combined action of B sticking and agent A moving south, and the last one is just for agent A moving south. Challenges with this project were many, and I was not successful in reproducing the slides, but I'll tell you how far I got. Initially, I had tremendous problems with my virtual machine. It was a 64-bit machine, and I found out from repeated errors and from looking at similar posts in Piazza that it was sort of a known problem. So I ended up migrating to a 32-bit machine, and from there I was able to get the code to execute. The details in the learning and the paper were sort of vague. They don't really give you the specific learning rate or decay rate, so I had to make some assumptions there. The documentation for this burlap code is there's not a lot of example codes to use from, not a lot of details on how to debug it. And with so many things being built in, it's really hard to see what's going on in the background. And for this particular game, it doesn't exist already in burlap, so I was required to try to modify some of the existing burlap code to get this game sort of working properly. And what I attempted to do was write code for describing the ball possession as an attribute for the agents. I tried to write code in the mechanics jar file to handle the transfer of the ball, but I'm not sure these were successful. So here's the results. For regular Q learning, I used a naive Q learner, and each learner worked independently. For agent A, this is the value of the state action pair described, agent A moving south from that initial position. As we can see, and as was mentioned in the paper, the Q values don't really converge. They continue to fluctuate. However, in the paper, the fluctuations seem to reduce, but in my sample here, they don't really decrease. The oscillations kind of stay constant. For friend Q, I did get a similar looking chart where there is convergence. It does convert to a specific Q value. My convergence rate was very quick as opposed to that shown in the paper. I was unable to get the utilitarian Q to execute or the faux Q to execute. And I think the reason was that the code I was trying to write in for what was needed to replicate this game, I don't think I executed that properly. I think there are probably some bugs in how it's working. And I basically just ran out of time trying to get that to work right. I just ran into so many problems trying to get this thing started that this was the best I could do with it. Thank you.